Come with me, if you will, on an imaginary journey. Suppose you were sitting in this room in 1855, when the Christmas lecture was being given by Michael Faraday. It's not so long ago. Perhaps your great-great-grandfather was here as a very young man, if you can imagine such a thing, listening to the Christmas lecture at that time. Naturally, there was no electric light to switch on and off, and the only heating was provided by a fireplace behind me, but now dismantled, provided the heating. It was rather cold outside, and when people left, I dare say, they were warmly wrapped up for the journey home. Some perhaps walked a long distance to get there. Others, more fortunate, were drawn up into horse-driven carriages, and all, I expect, were restored by a hot meal, cooked on an open fire or perhaps a stove when they got home. Impossible, of course, to telephone your friends, to listen to the radio or to watch television. And as for next week's visit to your favourite cousin in Brighton or your elderly aunt in Edinburgh, they were not expeditions to be taken lightly. A little time before that, the announcement was made for the Manchester horse-drawn coach, known as the flying coach, which plied between Manchester and London. And it announced, and I quote, "However incredible it may appear, this coach will actually, barring accidents, arrive in London 4.5 days after leaving Manchester." Things, of course, have moved on since those days, and we have to stretch our imagination greatly to realize what the changes have been. If, however, you try out a few journeys in time, choose your own period, it's all in the books, you may have a few surprises. And the surprises will be as nothing compared to the surprises that are in store in your own generation. You might like to guess what transport, communications, perhaps space travel, materials, energy, and so on, will be available in the years to come. And if, when you reach the advanced age of 50, you find that perhaps you got a few things wrong, do not be distressed, because you will be in excellent company. Many well-informed observers have confidently predicted that the motor car, the incandescent lamp, heavier-than-air flight, space travel were quite impossible. Developments that later became commonplace were, at first, of course, merely a gleam in the engineer's eye. Engineers like Hero of Alexandria, George Stephenson, or Frank Whittle. It is, of course, the business of the engineer to have these ideas about how to do things, and then to turn these ideas into reality, and it can be a very exciting business. Take, for example, the development of the steam turbine by Charles Parsons. Charles Parsons developed the world's first successful steam turbine in 1884, that's 100 years ago. And this is a model made by Charles Parsons and his colleagues at Newcastle upon Tyne to 1/3 scale. It's actually a working model. It looks rather small, but it's got all the components made up very carefully. Now, if you look at the machine, you can see that there are two principal parts to it. The mechanical turbine end is on this side, and the electrical dynamo, which produced the electricity, is at this end. And the two are coupled together directly. The way the machine works is by way of steam pressure. The steam comes in down a pipe from this point into the turbine casing, and then it moves through these rows of blades which are attached to the rotor. The casing, of course, is closed at the time, and there are sets of blades, which perhaps you can see on the inside of the casing, which fit neatly in between the blades in the rotor. The result is the steam passes through the blades, the rotor is turned, that drives the dynamo, and electricity is produced at the other end, 7.5 kilowatts. This was an incredible machine. The original is in the Science Museum in Kensington, and you might like to see it there. It rotated at 18,000 revolutions per minute, an extraordinary feat of engineering. And it was said, rightly, that on the development of this kind of machine, it was possible then to produce power 100-fold for the same weight of machine compared to what was available beforehand. A very remarkable development. We can show you the current version of an electrical machine, and the turbine, this is the turbine that drives it, producing 660 megawatts of electricity, enough to supply a city from a single shaft. That's in the process of construction. And to give an idea of the scale of the thing, this is a blade, a single blade, at the low pressure end, that's the far end of that machine, and there are many of these blades sitting around the wheel being driven around by the steam pressure. Parsons also applied his ingenuity and his turbines to the propulsion of ships. His team at Wallsend produced a historic little ship called the Turbinia, which could travel at 34 knots in 1897. It was the first ship to be powered by steam turbines of that kind. Not at all bad for 1897, but the Navy was not impressed, and in order to make the action go forward, Parsons and his team gate-crashed a great naval review being held in Spithead to celebrate Queen Victoria's Diamond Jubilee. And the little ship, the Turbinia, raced down the line of the mighty warships and created a sensation. Naturally, he'd proved his point, and shortly after that, steam turbines were adopted universally for use in naval ships in this country and also abroad. Now, the story of machines is almost as old as the story of man, and ancient civilizations made good use of simple machines like levers, pumps, and many other machines as well. By the time of the Renaissance and Leonardo da Vinci, machine design was making rapid progress. Leonardo left behind 5,000 pages of sketches and illustrations of machines, well ahead of his time, and we can show you a few of these by way of example. Here we have a hand-driven winch for raising a weight. The next one shows a self-centering thrust bearing, very ingenious and simple design. The next one is quite an amusing one, and Leonardo was preoccupied with the multiplication of action by mechanical means. And I dare say that that drum, with 3 drumsticks operating off the single crank, was a very effective and noisy drum. This is a very remarkable sketch. It's believed to have been drawn by a student of Leonardo's, and you can see that although it was drawn a long time ago, there's a very close resemblance to the bicycles that you saw about perhaps not so very long ago. This was a machine that, alas, never flew. It was copied with much enthusiasm by many inventors afterwards, but never achieved any significant success. Leonardo contrived these machines without any knowledge of what caused things to move. The engineering at that time was in the imagination of the designer, and the sciences had not developed to a point at which they could be used for purposes of design. Now, motion, whether of machines, of living creatures, high up in the atmosphere or deep in the sea, is of great interest to many people, and we have a little film to show you some of the perhaps spectacular motions of the past. This is the 3rd successful moon landing, and the 2 astronauts, Ed Mitchell and Alan Shepard, were busy on the surface. This is a very slow motion, but a very important one. The tugs are drawing an oil rig into the Murchison field, and you see that the engineers are watching anxiously that this 24,000-ton structure should be dropped precisely in the sea, the right way up, at the correct time. And down she goes. And shortly you will see looks of great relief on the faces of all those concerned that all has gone well. There are 3 very happy men. This is a natural motion. It's a storm breaking over the breakwater at Alderney with huge waves being driven up by the wind, and yet another storm showing very complicated natural motion at B Sands in South Devon. You can see the light still in one house where the householder was clearly determined to hang on to the last. And these huge waves were breaking over the houses. All these motions can be very complicated, although the fundamental laws are simple, but the application of the laws to complicated motions presents very difficult problems. And where the engineer is involved, he not only has to understand how these things may happen, but he has to make things happen. He has to make machines move in an orderly and controllable way. Now, when we are thinking about how to describe how things move, then we have to think in rather specific terms, and I'll illustrate that by one or two examples. If I drop a ball, for example, it merely falls under gravity, and in a fraction of a second, its displacement goes from this point to that point. We can represent that by a vector, which is simply an arrow, drawn from the top point to the bottom point. Its length is the displacement, and the arrowhead will show the direction. That's called a vector quantity. In the same drop, the ball will have a set of velocities on the way down. They will increase, and we can represent the velocity at one point by another arrow. Again, it's a vector quantity. Go one stage further, the ball is accelerating downwards, and we can represent the acceleration by a symbol of vector. And the importance of vectors is very wide, and we can demonstrate how they can be used very effectively by turning to a historic experiment of Leonardo da Vinci. Leonardo wanted to measure how fast things fell under gravity. And to do so, he made an arrangement rather like this. A number of drops are being released at regular intervals from the little tube, as you see there. And if we bring the clapperboards together, they will stop the drops at various points in the fall. And the marks that are left then on the paper will show how far a single drop would have fallen in those successive time intervals. So Mr. Coates will now clap the boards together very smartly, and we have a number of positions marked out, which we'll now proceed to measure. Here's drop number 1, here's drop number 2, drop number 3, drop number 4, and drop number 5. Now let's think about velocities. In moving from that point to that point, in the period of one drop, how many drops per second, Bill?
10 per second.
10 drops per second. So in a tenth of a second, a drop would have fallen from that point to that point. Its average velocity will be the length of that distance, and if we cut that off at that point, we can represent that velocity as a little vector and put it up on the board so that you can see how it changes. In the next tenth of a second, it will have traveled that distance. Then we cut that off, and perhaps we can take one more. In the third interval, the average velocity would be proportional to that length. So if we cut that off, I think that'll be enough, probably. If we put them up with the base at the same level there, we might need to do it a little higher. And one more. Then those are the three velocity vectors proportional to velocity at these successive intervals of time. Now, of course, the velocity will have changed. That's a small velocity, larger and larger. The drop accelerates. Now, the difference between these represents the acceleration. And so now we measure the difference between these successive velocities and the change in velocity. Can I just mark? We'll actually measure the acceleration in a minute, and that's about average, I suppose. So if you cut it off there and measure that and tell me how many centimeters involved.
About 9.5.
It's about 9.5 centimeters. Now, we have to put a scale factor in now because it's not every second between drops, it's a tenth of a second. And in order to get the acceleration downwards, it turns out we have to multiply by the square of that magic number, 10. So if we multiply, you said 9.5 by 100, the answer is 9.5 meters per second per second. And that would be our measurement of the acceleration of these drops falling under gravity. Now, I expect most of you know the acceleration of gravity without any air resistance is very accurately measured. And the correct values are shown there. Slightly different, you see, for Newcastle and London. In fact, the population of Newcastle is slightly heavier, curiously enough, than the population of London. And the nearer the equator you are, it turns out the lighter you get. It's a point you might bear in mind. But that wasn't a bad experiment, the experimental result, I mean. 9.5 against the actual values measured more accurately of 9.8 meters per second per second. Well, the talking about vectors, we have to think sometimes of velocities that are not in a straight line. These, of course, are the straight line velocities. And here we have a little demonstration of that. If I put the overhead projector on, and if you think of a point moving around a circle at a constant speed, you'll see that as it moves, then the direction of the velocity represented by the little blue arrows actually changes as it goes around. And so we have to ask, well, what's the difference in those velocity vectors? And if I put that in about that position, where you can see it, those are the two velocity vectors. The difference between those two now lies in the different direction from the velocity. It goes in that direction. The change in velocity, of course, is the acceleration. And now the acceleration is in towards the center of the circle. A well-known result, but remember that the acceleration need not be in the same direction as the velocity. We'll be using that fact later on in the lectures quite a bit. Before we leave drops, though, you might like to see a little film which shows how drops are used in modern technology. And this film is of a printer which produces little jet drops of ink, 100,000 per second, directed at the paper. It prints very fast, 100,000 drops per second. And they are moved by a controlled electrostatic field through which the charged particles of ink are made to travel under the control of a computer. The printing is very fast indeed, and there's no actual contact with the paper. A very elaborate development of drop mechanics. A lot of engineering and a lot of science has gone into that. Now, an important property of vectors is the way they add up. Think of a force vector, two forces pulling. An important question is that if this represents one force in that direction, that's force 1 vector, force 2 vector, both pulling on that pin there, let us say, what is the resultant effect? And I expect most of you will know that the resultant effect is shown by this vector made up in the diagonal of that parallelogram. Now, if we change the direction of the forces, then, of course, the resultant changes. When the forces are in line, it's simply the addition of the two separate parts. But when they're not in line, in fact, when they're opposed, then the resultant can be quite small. If those two forces were equal and pulling in opposite directions, the resultant, of course, would be 0. We can illustrate that with a little tug-of-war experiment. So let's have some volunteers, please, who will demonstrate their great strength with the tug-of-war and also illustrate this interesting property about force vectors. We have 3 strong young men on the end of the rope, one end of the rope. The other end of the rope is securely attached, provided they're not too strong. Could you move around just a little bit so that you don't catch on the end of the table? That's perhaps better. And if you put a load on that, then we'll see how it all works out. Now think of a little piece of rope. Go back a bit, if you would. A little bit of rope in the middle is now under tension that way from that side and tension that way from the railing. And what I contend is that this young lady, whose name is? that Katie will be able to pull these three very strong chaps forward, despite their great strength. Would you like to lean backwards a little bit? And you've got rubber shoes on. That's cheating a bit, but still we'll... Now, if Katie would like to be the resultant force of these two nearly balanced forces and pull this way, then I would think you can pull them forward quite easily. Give them a good tug. I'll give you a hand. I think it's their rubber soles are doing it, but you can see that we can exert... Let's try it once more. You pull on that side. Okay, very good. Thank you. Curiously enough, if we ask about the physical nature of forces, we get some curious answers. Outside the nuclei of atoms, only two kinds of forces are known in the entire universe. One is the force of gravity, and the other are electric forces. All other forces are made up of one or the other of these kinds of forces. Physicists using elaborate equipment are now investigating how the forces inside the nucleus are related, if they are related to these forces we know on the outside. Electric forces account for much of our ordinary experience. And although it may seem strange that that is so, when you think of pushes and pulls and pressing on things and so on, if you remember that materials like this diamond material is made up of a number of close-packed atoms with electric forces in the nucleus with a positive charge and electrons around the nucleus with a negative charge, then any attempt to displace the structure is resisted by the forces which apply between the various charges within the material. And these produce a wide variety of forces that we experience in ordinary life. Those forces control the deformation of the material. As to electrostatic or electromagnetic forces, they too depend on the existence or the movement of electrons. A very familiar example, of course, is if you rub a balloon with a cloth, you actually rub off electrons, leaving the balloon with a net positive charge. That balloon now should be reasonably charged up, and if I give it a chance to attract charges from some other place, then given the chance it will probably stick reasonably well by pulling up the electrons through the young man's hair of mutual attraction. Please keep the balloon if you like. When electrons move along wires to form the electric current, then they exert forces on current-carrying wires in their vicinity along a rather similar principle. And that principle, that is the interaction of these electric forces between wires carrying electric currents or between wires carrying currents and permanent magnetic fields provided by permanent magnets here, can be illustrated by this very neat little experiment that Mr. Coates has built up. Here we have a coil of wire made up of many turns mounted on the frame, and we can connect it to the battery such that current will flow through the wires. There's a switch or a commutator arranged at the bottom end such that the current always flows in the same direction on the coil that's on this side of the apparatus, upwards here and downwards there. And when they exchange their position, because of the switch, the current still comes up on the one side. As that current-carrying wire goes through the magnetic field of the two magnets, the forces of the kind I've just mentioned are exerted. And if we turn the battery on, then the forces act on the magnets. They remain stationary, but they drive the coil around. And that is the basis of that vast family of machines, electric motors. Now, if we do the other thing, and if we do not put current through the wire, but simply turn the wire in that magnetic field, then a current will be induced in the coil which you can see flickering on the microammeter there, as the result of the interaction and the induction of current in the moving coil. That principle, of course, was discovered in this very building by Michael Faraday and forms the basis of the practical generation of electricity upon which the world now depends. British Rail are developing trains that fly. No wheels. They lift off the rails to a constant gap, 15 millimeters, by powerful electromagnets, which we can illustrate by reference to this little ball, which is an ordinary beach ball to which there's been attached a metal cap capable of attraction by this electromagnet, which I will shortly switch on, and then the ball can be held up against the magnet. So if I switch the mains on, the electromagnet is now activated, and if I put the ball within the range of the magnet will pull the ball up, and it will actually stay fixed against the magnet. If I try and pull the ball away, it's quite difficult, but with a good pull it'll come. And if it's too far away, it will fall. If it's too near, it will simply bump up against the face of the magnet. So it's rather unstable in any intermediate position. And what British Rail would like to do would be to have a suspension which held the ball or the train at a fixed gap. Now that can be achieved if you have a light system here going from this light to a photoelectric cell, which actually controls the current in the electromagnet in such a way that if the ball goes towards the magnet, the current is made less and the ball falls away slightly. And conversely on the other side. Now if I can start it off in the right position, it will in fact hold that gap, which I hope you can see, quite closely, and I can turn the ball without any interference, and that's the principle of magnetic levitation. Now it's not enough just to get the train off the rails, of course, the train has to move. So how about that? Well, for that, the proposal, and indeed the result, is to use an induction motor, a linear induction motor. But first let's look at an ordinary rotational induction motor, which is shown here. It consists of a casing, a number of electromagnets are spaced around the casing, and alternating current is fed into the magnets in such a way that a magnetic field is swept around the casing, rather like a brush with bristles pointing inwards, rotating at a speed determined by the frequency of the current. Now, that magnetic field intersects elements in the rotor and induces currents according to the experiment that you've just seen. Those two currents interact with certain forces. The forces can't move the stator, but they do in fact drive the rotor round in pursuit of the electromagnetic field. And that's the principle of an induction motor. However, the train has to move in a straight line. So the next stage is to say, well, we'll make this into a linear machine. Imagine that this casing is the stator with the electromagnets spaced around it, and if I cut through the casing and lay it flat, then I have the basis of a linear induction motor. The poles are now spaced along the length rather than around the circumference, and by feeding alternating current in the correct phase along the length, then I get a traveling magnetic field which drives the rotor or some small object picking up the induced electricity in that direction. And Professor Laithwaite has kindly provided this little demonstration for that. The electromagnets are, in fact, within this little black box. If I switch it on, I produce a traveling field going to the right, and if I put this copper tube in position over it, stop it initially, then it will drive the rotor round and round as the forces affect the lower part of the tube and put it into quite a fast rotation. However, that's not quite the answer yet, so to get the train to move, then if we put that plate on the top, I'll switch the machine off to begin with, so everything is nice and stationary, and if I now switch the machine on, the traveling field will now drive the plate off in that direction. You're quite safe. It doesn't go that far. At least it hasn't so far gone that far. And it fires away. So that if we had a very long track with electromagnets spaced out appropriately, then we could, in fact, drive the train with that propulsion. So the combination of these two effects can be illustrated with the little film that British Rail have made up about their maglev train. That's part of the linear induction motor, which is suspended above the electromagnets providing propulsion. Those are the electromagnets for lift. It's lifting off and now driving forwards. And you can see that it can negotiate quite a considerable gradient and also take a turn in its stride. So there are many important potential applications of induction motors ahead which have yet to be developed. Well, in these lectures, we've had a quick look at some of the basic forces and their characteristics so far. And now I want to look ahead a little bit and say what we shall be talking about for the rest of this lecture. We'll be looking at things that move, including living as well as mechanical machines, living machines in the later lecture. And sometimes the design and the motion may be surprising to you. And we have a set of film which illustrates some of these matters. This film is taken at the Motor Industries Research Association, in which cars are subjected to various kinds of special motion to determine their characteristics. Vehicle is going through a water trough. A very bumpy ride. Perhaps a typical country road. The APT train showing the tilt mechanism at work so that the passengers are kept in comfort as the train turns curves at high speed. We shall come back to that later in another connection. And a very famous machine, the Harrier jump jet, taking off from a 6-penny bit, so to speak, and climbing up very rapidly. Here we have the takeoff of the European space rocket Ariane on a successful firing. Its intention is to put communication satellites into orbit, and there are some very major problems of control. A different kind of flight. The cyclist is pedaling busily away and driving the propeller in the Gossamer Condor machine. And a rather unusual type of bicycle. It is, of course, up to the imagination of young engineers to think how to improve the bicycle. It's been around for a long time, but there may still be variations of the bicycle that you will be inventing in the future. The subject as a whole is called dynamics, and it has two principal parts, kinematics and kinetics. Kinematics deals with relations between positions and velocities, whereas kinetics deals with forces. Consider that humble but efficient machine, the bicycle, to illustrate the different parts of the subject. If we could have a volunteer, perhaps, to... You ride a bicycle very confidently? Your name is?
Madeline.
Madeline. If Madeline would like to try her hand at this, we can illustrate one or 2 points. Firstly, if you ask how far the bicycle will move forward for one turn of the pedals, that depends on the gearing of the bicycle, the wheel diameter, and so on, then you're talking about kinematics. If you ask how hard Madeline has to push on the pedal to accelerate herself with a given acceleration, then you're talking about forces, and that's kinetics. And if you ask how Madeline can stay up without falling over, assuming you can, then we shall be into kinetics with a vengeance. Would you like to have a try at that? Turn the corner. That's not bad. Thank you very much. So if we keep those aspects of the subject distinct as we go through, then we shall be thinking about kinematics on the one hand and kinetics on the other. Let us look at the kinematics of gears. Gears have been around for so long that they often pass by without notice, and yet they're a very important part of many machines. As you know from traveling in motor cars, people change the gears all the time, and in doing that they change the transmission from one set of gear wheels to another set of gear wheels. And here we have an illustration of that arrangement with two spur gear wheels, two simple spur gear wheels, lined up as you see just now, and of course they will go at different speeds. I expect you will decide very quickly that if I turn the wheel on this side, then turn the big wheel, then that will go more slowly than the small wheel. But the question is, what's the speed ratio between those two? And that, of course, depends on the number of teeth. But you should be, which is printed on the wheels, but you can't see that. Now, if I turn the big wheel, perhaps those on this side of the room would count the number of revolutions of that wheel, and those on this side of the room would count the number of revolutions of the other wheel. I hope you can see it. I'll give you a better chance to see it. And then we'll compare notes when the two markers come back into coincidence, and we're back essentially where we started. So if I turn rather slowly, I hope you will start counting now. And now they're back in coincidence. So if we hear from that side of the room as to the number of revolutions of that side, the average is 11. And on this side, 15. They're more confident on that side. I don't know why. 15. In fact, it's 11 and 15. And on this wheel, there are 150 teeth. On that wheel, 110. And the ratio of the speeds depends on the number of teeth, which depends on the diameters. And of course, it's the little wheel that goes the faster. Now, gears in combination can be made to produce a variety of different speed ratios. And here we have such an arrangement called an epicyclic gear train. And we can investigate how it works by just turning it around on this overhead projector. So there, I hope you can see that. And now we'll start to do some measurements. There are three principal elements. There's the big green wheel on the outside that I'm just touching. There's a combination, orange in color, in the middle, with three wheels and a central ring. So that's the second element. And the third element is the sun wheel sitting in the middle. Now, how does it work? Suppose I lock the orange combination. That cannot turn. And if I now turn the outside wheel through one revolution, you can see the sun wheel goes in the opposite direction. And if you're counting, when we come back to starting point again, you will probably have counted that the sun wheel went through 3 revolutions, so 1 revolution of the outer wheel. Speed ratio there of 3 to 1. But now we can take another combination, and now I'll fix the outer wheel with this little peg. That's now fixed. And turn the orange wheel by a means that you can't actually see, but it's connected to an invisible or transparent plate underneath. And then you can see that now the sun wheel and the planet wheels, that's the orange combination, turn in the same direction. And if you're counting, when we come back, something is smoking here. Thank you. I think our induction motor was overheating there. Then we come back to the same position, and I expect you were distracted there, but the speed ratio between those two parts was 4 to 1, and they were going in the same direction. And finally, if I fix the sun wheel, then it's a rather more complicated result. And if you're still counting, you'll see that when we're back to base again, the outer ring is turned 4 times, and the planets, the orange ring, is turned 3 times, 3 to 4. So by playing various tunes on that, one can obtain various gear ratios. Very important, where you need to have flexibility in the gear drive over a fairly wide range of gear ratios. Now, that's to do with the gears as a whole. But if you think about the shape of the gear teeth, then you find that there's some very interesting questions to be resolved. In earlier times, gear teeth were very crude and simply consisted of spokes sticking out from the periphery of the wheel and engaging with similar spokes or with a lantern arrangement, as in B there. And this craftsman of the 16th century was driving the crank around. He had a speed reduction between those two, another speed reduction between those two, but then he had he was geared up in speed between those two, so that either the artist was taking some license in the matter, or he could have done away with all of these and just used those two to get the same result. But we shall never know. However, the point to note is that the gear teeth are simply short spokes, not a very effective transmission, because with spokes like that, then there's clearance and you don't get smooth transmission, which is essential in most machines. So let's see how we might do that. Now, suppose we take 2 bodies of any shape, one pushing against the other. And suppose that this one is pushing that one round. There'll be a certain speed ratio between the two of them. And it turns out that the speed ratio depends on the position of that point Q, which is the intersection of that line normal to the 2 surfaces where it intersects the center line. Now, if that position stays the same as the things turn, we get a nice constant speed ratio, but these will not do it. If I just move them very slightly, then the next position of that normal line intersects at Q2, and there's a different speed ratio. So these would not proceed with constant speed at all. The question is, what should the shapes be to make sure that the speed ratio remains constant? And this is one answer widely used for gear teeth. And we'll actually construct some gear teeth now so that you can see how the construction goes. That's the gear wheel that we start with. It's only half a gear wheel, but it'll do for our purposes. And the construction of the shape of the teeth goes rather like this. Let's put that in that position. I take a string and tie it to the end of a circumference known as the base circle, put the string taut around the circumference, and then with a marker unwrap the string, and you see that it traces out a certain curve. That curve is one flank of the gear tooth that we are designing, as we shall see in a minute. To get the other flank, I repeat the process from the other side and have a second string marked around, and now mark the second flank. And so now we have the prospect of a gear tooth in mind. Now I take off the base circle, and now I am in a position, with the help of Mr. Jameson, to assemble the teeth. So we'll busily put the teeth in. There's the one we've just designed, and in it goes. And now we put the others, and they're identical, and they could be marked out in exactly the same way. So there we are, ready now to engage with the similar wheel on the other side. So we're about to drive these two together and see whether that important line does in fact satisfy the conditions we want. What I'd like you to watch as we turn the wheels is that point, which is the point of contact between the two teeth. And you will see, I think, that that line, which is normal to the two surfaces, intersects the center line at the same point wherever the teeth are. And that's the property of these teeth, which are known as involute teeth. So if I now turn my wheel, Mr. Jameson turns his, if you follow the line, and the point moving down the line, you see that that's following it very accurately. And now the next two teeth are coming into engagement and are moving down slowly down the same line. The line doesn't itself require any adjustment, it's fixed. And so around the circle. So with that combination of shapes, a smooth transmission, constant speed ratio is assured. It's an illustration of the geometry, sometimes the very interesting geometry that gets involved in quite ordinary mechanical parts like gear teeth. And obviously it's very important that they should work very well. The actual design of gear teeth is a bit more complicated than that, of course, because the designer has to think of the loads, the forces, the wear, lubrication, and so on. But so far as the kinematics goes, then that's how the kinematics works out. Not all gears, of course, need to be circular gears. And just for fun, we've made up a few gears which are non-circulars, slightly unusual shapes, to show that if you get the geometry right, or the kinematics right, then you can in fact produce continuous transmission, even though it may not be of uniform speed ratio. And you see these two turn very neatly, one with the other, and the shape is so designed as to allow them to do that. And we can go further. We've put together some nearly square gears, shown here, which perhaps even more surprising. And if I turn those around slowly, you see that the two shapes correspond very closely to each other. So with the appropriate teeth shapes, then again you can get a continuous, although perhaps not a very smooth transmission. And a wide variety of such shapes are possible, although of course they are chiefly curiosities. Another very important kinematic problem, to which there are several solutions, involves how to change circular motion, something going round all the time, into linear motion, something moving in a straight line. That happens in many machines, as we shall see in a minute. And one way of doing it is by use of a cam, and this little apparatus demonstrates the cam. If I switch it on, then an electric motor is driving the circular plate, and there's a shaped cam attached to it that goes with it. Now, that's pushing the follower from side to side as it goes around, and the motion of the follower is being marked out on the graph paper. The designer would have to determine what shape that cam should be to produce a given motion of the follower. Very often, these devices are used to produce precise movement at this point to correspond to a certain angular position in the cam, as indeed in engine camshafts, as we shall shortly see. So that's turning circular motion into straight line motion. In the reciprocating engine, the requirement goes the other way. And here we have a very nice model of an engine made up by Mr. Jameson to illustrate that point. With a reciprocating engine, say a petrol engine, the problem is to change the up and down motion of the piston into the circular motion of the crankshaft. So you get power out and drive to the wheels of the car, for example. Now, in this model, we're not actually driving with combustion, so I'll have to turn the handle. But the kinematics is the same. And it's done, of course, by way of that part, which is called the connecting rod, and this part, which is called the crank. And they move in the way that you can see. And that's the basis of the reciprocating engine kinematics. Now, the actual engine cycle involves drawing in petrol-air mixture, burning it, and then exhausting it from the cylinder. And the way the cycle goes is shown on the picture there. And I'll go through that with you, and then I'm going to ask for some volunteers to come up and help me to do the appropriate actions at the appropriate time. So rather slowly to begin with. Here the burnt mixture is being exhausted, then I have the exhaust valve, that's that valve, open. So the burnt gas is now being pushed out. Shortly before the top dead center position, the inlet valve opens to allow the petrol-air mixture to be drawn in. The exhaust valve is meantime closed, and that's drawing in the petrol-air mixture into the cylinder. Then the inlet valve closes. We're coming up on the next line of the cycle, and the gas is being compressed. Near the top of the stroke, we have ignition, and the spark in the spark plug then burns the mixture, which expands very rapidly, and that moves the piston down very powerfully. That's the power stroke. The exhaust valve has to open and release the mixture, and that's how the cycle goes. But now, to help the volunteers to work it, I have a little machine here which actually produces noises. That's top dead center, that's bottom, that's inlet valve open, that's exhaust valve open, and this is the flashing light. So if we could have some volunteers perhaps to come and help with this exercise. Would you like to, you come over here and you handle the ignition, if you wouldn't mind, and try and do it when we follow the right timing. Would you like to come and do, your name is?
Peter.
Peter?
David.
And David, would you like to do the inlet valve, and would you like, your name is?
William.
And William, to do the exhaust valve there. So we can tell when you're doing it because we can hear you, you see. Right, so here we start. Now we'll have the exhaust valve open. Keep it down. And it's coming up on the stroke, upstroke. Now we want the inlet open. Now its inlet closes, ignition, and then the exhaust opens, and the inlet opens. Okay, now I'll speed it up a little bit. Could you try and follow the cycle? Open, close, ignition, open, and so on. And you get a succession of funny noises coming out. And thank you for your help. Another linkage, much used by the designer, it involves 4 bars. And if we have the 4-bar linkage available, the British Rail linkage, then, but before, well, that's coming in, let me just show you how it's actually done in practice. This is an engine which has been cut away to show the parts. We'll just look at it very briefly. There are, in fact, 4 cylinders, rather like the one that you saw a minute ago, and a succession of valves which are opened and closed, not by volunteers like Peter and David, but rather by a belt driven off the crankshaft to the camshaft, which, using the cam of that kind, pushes the valves at precisely the right time. So the performance of the engine is controlled very largely by these timing requirements. Now, the 4-bar linkage is very widely used, and one application is in British Rail's APT. The tilting mechanism consists of the carriage itself. Passengers are sitting in here. The acceleration as it goes around the curve is measured by a little instrument, and that activates some hydraulic jacks which move the carriage from side to side according to the signal picked up by the accelerometers. In our model, we're actually turning the carriage. But the 4-bar linkage, which is a very simple mechanism, is a very useful mechanism, particularly when carefully controlled movements of this kind have to be provided. Then another kind of 4-bar mechanism I can show you here. It's one we've put together ourselves. If it is actually plugged in. Just drive one end. You can see that the bars move in a certain way, and the object of the design here would normally be to arrange that some point on the bar, this bar called the coupler, moves in a certain way, a certain path. In this case, it's producing a straight line for at least part of the motion. We can do it with the overhead projector perhaps equally well. If I mark the line here by a pen, then I can trace out curve number 1 by moving the position of the pen, obtain a different curve. And if I were the designer, I would need to decide the sizes of the links and where the pen should be to obtain the curve of the kind that I would like to get. Here there's a great variety that can be achieved, and so on. So the designer has plenty of scope there, and that scope can be extended by use of computer techniques, which we can illustrate by using this little computer here. We've set up on it the software which enables the designer to perform that kind of operation in a very flexible way. So if we have the linkage on the screen, which we do, I hope you can see that on the monitors, and if we have the volunteer who would like to come forward, we can ask him if he'd attempt to change the design of the linkage. And your name is? Oliver. So Oliver will now see if he can, first of all, make the linkage turn around. The right button to press for that is that one there. So if you give that one press, then you can see that the linkage is generating a certain curve. But perhaps Oliver's not very satisfied with that. And he would like instead to change the shape of the curve. He's looking for something that cannot actually be calculated by explicit mathematics. Now, what shall we change? Suppose you press, say, that button 3 times, and then make it run again. And now he's produced another curve. One more time on that, and see what the change this time is, and run. And by that means, it's possible to generate a very wide range of curves very quickly to see if you can satisfy the actual requirements of the output point. Thank you very much, Oliver. But the most advanced linkage ever developed works in 3 dimensions. It has not just 4 bars, but it has more than 200 joints capable of moving in 3 dimensions under precise control of a single computer. This is a very familiar machine. There are about 60 million in this country alone. And I'd like to introduce you to our machine, which does this spectacular performance. And if you count the number of joints that you have available, you may find that you have more than 200 available, and it's all under the control of the computer, safely inside your head. We shall be looking at the motion of living machines later in the lectures. In the next lecture, we shall start to think about the effects of forces upon things that move. Thank you.